So here is a question for you. The question is saying a steel block weighing 12 Newton is pulled up an incline plane 20 degrees above the horizontal by a constant force of 7.35 Newton, which makes an angle of 10. This is supposed to be 10 degrees above the incline plane. The block starts from rest and is pulled 2 meters along the incline plane. The coefficient of friction between the block and the incline is 0.20. Determine part A, the work done by the block, or the work done on the block by the force. Part B, determine the increase in potential energy of the block. Part C, determine the increase in kinetic energy of the block and the amount of work required to overcome the friction force. Okay, so now let's start with part A, which is saying the work done by the force. So now this force, it was applied at an angle. Okay, so we know that work is force times distance, but in a case where the force has been applied at an angle, you get the component of the force which is going to be in the same direction with the displacement. So as we can see, the distance is in this direction, so we have to get the component of that force which is going to be in the same direction as well, so which is going to be Fx. So therefore it's going to be the work done by the force is going to be Fx times d. So using SOHCAHTOA, we can see that Fx is going to be F cos theta. Okay, so we have this force in short here. We can just see here, we can see that we have this and also that. So we have Fx and Fy. Okay, so Fx is F cos theta and Fy is F sin theta. This is going to help us again. Now another thing which we have to take note here is that so we have the angle which is 10 there. So the work done by the force is going to be F cos theta times the displacement. Let's plug in the values. We see the work done by the force. Okay, so we can see that the work done by the force is going to be, the force itself is 7.35 cos 10 degrees times the distance is 2. So we're going to have 7.35 cos 10 times 2. So I'm getting my work done by the force to be 14.47. So I'll just say 14, it's 14.4766. I'll round it off and say 14.48 joules. So that is the work done by the applied force. So I'm going to say the work, I'll put it here. The work done by the force is 14.48 joules. Now we are done with part M. Let's go to part B. Part B is saying determine the increase in potential energy of the block. So how do we determine the increase in potential energy? So the increase in potential energy is the same as the change in potential energy. So the change in potential energy is going to be the potential energy final minus the potential energy initial. Okay, now initially we don't have initial potential energy because it was starting from this point here where the height is going to be 0. As we can see from here, we can see that this is going to be the potential energy is mgh. Now in that case we're going to have mgh final. Now that final is the one which is going to be increased all the way up to this point, which is going to be this h, but the h here is going to be 0. Okay, so I'm going to say minus the mgh initial. Now the h initial at this level, it was 0. So the we don't expect to have the h initial. So this is going to be cancelled. So the change in potential energy is going to be just mgh final. Now this h, how can we find this h? Remember, we have been given uh, the distance here. This distance here is 2. We also have the theta. Okay, so you can see that the h is going to be the opposite over hypotenuse. So if I use sine theta, which is going to be the opposite is h, the hypotenuse is d, which have been given to say is 2. So to find h is going to be 2 sine 10 degrees. So where there is h, I can replace with 2 sine 10 degrees. Okay, so this is what I'm going to do. I'm going to say the change in potential energy is going to be mgh. Now this h, I'm going to replace h with 2 sine 10 degrees. Okay, so let's go ahead and find the answer now. So the change in potential energy we expect to have, do we have the mass? Now the mg, we have been told that a steel from here, a steel block weighing 12 newton, that is the weight force. Mg is the weight force. Okay, so we have 12 times 2 sine 10 degrees. Okay, so 2 times 12 is 24, so 24 sine 10. What are we going to have? So we are going to have the angle here is not 10, sorry, it's 20. We are using this angle because 10 is for the force, but 20 is for the incline, so I have to use 20. Okay, so I have to use sine 20 degrees, even here sine 20 degrees. So I'm going to say 24 because 2 times 12 is going to be 24. 24 sine 20, which is giving me the change in potential energy to be 8.2. It's 8.208, so I can just say 8.21 joules. So this is the increase in what? In potential energy. That is the change in potential energy. Okay, so we can put it here. So the change in potential energy, which is the increase in potential energy, is 8.21 joules. Now let's go to part C. Part C is saying the increase in kinetic energy. Now here, remember the work energy theorem where we talked about the work net to be equal to the change in kinetic energy. Now we can use this because we can't just use this one direct, because this is going to give us the initial and the final. We don't have the velocity in this case, and we cannot find the velocity because we don't know the acceleration. Okay, so the only method which can help us to find the change in kinetic energy here, which is the increase in kinetic energy, is the work energy theorem. So where we say the work net is equal to the change in kinetic energy. Now we are trying to find the change in kinetic energy. Now how do we find the work net? Once we find the work net, that is going to be our change in kinetic energy. The work net is going to be the addition of all the work done in the system. We have got the work done by the force, so I'm going to say the work done by the force when this object was going up. Now there is friction. Okay, so I'm going to say minus, because that friction is opposing the motion, is going in that direction, minus the work done by the friction. But at the same time, we also have another force which is opposing the motion, the work done by the by Fg. So I'm going to say minus the work done by Fg. Okay, now what we have to understand here is this. This is the diagram which we have. Now this object is moving upward, so there is a work done by the force. Okay, that force is going to be positive. Now there are two forces which are opposing motion. On an incline, when an object is going up, always Fg is going to be opposing motion. So we are going to have the work done by the Fg. Now that one, since it is opposing motion, is going to carry a negative. As you can see from here, it has a negative. Again, we have the work done by the friction force. It's also opposing the motion, so it's going to carry a negative. Okay, so we have to find the work done by the force, which we have already found here, which is 14. Okay, so we're not going to find that. Now let's find the work done by what? By the friction force. So the work done by the friction force is going to be the force itself times the displacement. Now, what is the friction force in this case? Friction force is mu times the normal force. Now, we have to find the normal force first. Okay? How do we find the normal force? There we go. We have got the force which is going there. Again, the force which is Fy pointing upward. So the normal force is there. Remember, there is also the force which is moving upward, downward here. We have this force. Now that force is mg always. So this one we have to understand Newton's laws of motion. On an incline, we're going to have mg cos theta. Then we also have another force which is moving there, which is mg sin theta. Now on an incline, what we have to understand is that fg is going to be mg sin theta. Now in a case where an object, this object is not applied at an angle, the force is not applied at an angle, then the normal force is going to be mg cos theta. But in this case, we are going to have different thing. So we're going to say that the summation of all the forces acting in y direction, we have got the force which is Fy pointing upward plus the normal force minus mg cos theta pointing downward. Okay? So now my goal is to find the normal force. I can shift these guys to the other side. Since this object is moving in x direction, we can say that this is going to be 0. So this Fy is F sin theta. Then I'm going to have, since it is going up, it is positive. Normal force going up is also positive. So I'm going to have normal force minus, this is going downward. Now, F sin theta, the theta here is going to be 10. But the theta for cos is going to be 20 because we are talking about this. So this one, we are going to get this angle. And this one here, we are going to get the angle which is going to be what? 20. Okay. So now, I will just get rid of this to create space. So I'm going to see that if I shift the F sin theta, so I'm going to have mg cos theta minus F sin theta to be equal to the normal force. Okay, now let's plug in the values. Mg is basically 12, cos the theta is 20 in that case, minus F is 7.37 or 7.35. We have sin theta in that case is at 10. So that is going to be our normal force. Now we no longer need this. But remember that formula, we should not forget. Let me just put it here. The work net is going to be equal to the work done by the force minus the work done by the friction minus the work done by Fg. That is what is going to help us. So now, to find the normal force in this case, we can see that we are going to have 12 cos 20, which is 11 point. So I'm going to say minus, open brackets, 7.35 sin 10. So I'm getting 9, which is just 10 if I round it off. I'm getting 9.9999, which is just 10 newtons. Now we say that the friction force is mu times the normal force. So friction force is going to be, the mu value is 0.2 times the normal force, which is 10. So friction force in that case is going to be 10 times 0.2, which is 2. That is my friction force. Now, what else do we, after finding the friction force, now we are going to find the work done by the friction. Okay, so the work done, because we have to find the work done by the force we have already, which is 14.48. The work done by the friction force now, that is what we are looking for. So the work done by the friction force is going to be the friction force times the displacement. So the work done by the friction force is going to be, the friction force is 2, the displacement is also 2. Okay, yeah, so the displacement is also 2, so the work done by the friction force is going to be 4 newtons. So let's put it there. So the work done by the friction force is 4 joules. I'll leave it there. Now we have to find the work done by Fg. To find the work done by the Fg, it's going to be the work done Fg is going to be the Fg itself times the displacement. So the work done by Fg, Fg is mg sine theta, okay, times the displacement. Let's plug in the values. Mg is 12 times sine theta, which is the theta in that case is 20, because we're getting this theta here. So times the displacement. So the displacement is 2. Let's see. So we have 12, we can just say 12 times 2, which is 24. 24 sine 20, which is 8. So the work done by Fg is 8.21 joules. Okay. So 8.21, that was the work done by the Fg. Now, we can now plug in the values using our formula here. Let's see what we're going to have. So the work net, we are saying that the work net is equal to the change in kinetic energy. Our goal is to find the change in kinetic energy. So the work net is going to be the work done by the force minus the work done by the friction minus the work done by Fg has to be equal to the change in kinetic energy. So the work done by the force is 14.48 minus the work done by the friction is 4 minus the work done by the work done by the Fg is 8.21. Okay, this has to be equal to the change in kinetic energy. Now let's see what we're going to have. So we expect our change in kinetic energy, which is the increase in kinetic energy, to be 14.48 minus 4 minus 8.21. So I'm getting the work net to be 2.27. So the increase in kinetic energy is supposed to be 2.27 joules. Okay. Now another question is saying we have to find determine the amount of work required to overcome the friction. Now here we have already found, if you can check, the work done by the friction. That's what they're asking about. Okay, so the work done by the friction force, we have already found that is 4 joules. So you can even see here the work done by the friction force we have already found. So it is the friction force times the distance. So this was our work done by the friction force, if you remember very well. Okay, so we can just go through again. So we are saying the work done by the friction force, we are going to have what is our friction force? Is mu times the normal force, then times the displacement. Now in that case, what is our normal force? From our diagram, we said the normal force, we are going to say the summation of all the forces in y direction. We have the normal force pointing upward plus the Fy pointing upward minus mg cos theta pointing downward. Okay, so since we don't have any motion in y direction, the net force is 0. So we're going to have Fn. We know that Fy is F sine theta, but the theta is 10, but the mg cos theta in this case is going to be 20. Now we shift these two to the other side. We are going to have the normal force to be the mg cos theta minus F sine theta. Okay, now if we want, we can plug in everything here on this part here, or you can just find the value direct. So the normal force is going to be the mg is 12 cos what? we have cos 20 minus the force is 7.35 sine 10. So the normal force you are going to find that is, see, if you use a calculator there, we're going to have 9 times 9999 is 9.999, which is just basically 10. So the normal force is 10 newtons. Now let's plug in the values there. So we're going to have the work done by the friction. The mu is 0.2 times 10 times the d, which is 2. So we're going to have 0.2 times 10 times 2, which is 4. So the work done by the friction force is 4 joules. So that is it for this question.